Okay guys, in this video we are going to start the next focus, which covers simple mixtures. And this first topic, which we'll divide into two videos, covers the thermodynamic description of mixtures. And what we need to keep in mind when we talk about mixtures is that the composition of the mixture is also can also be regarded as variables of the system. So in this first bullet point, we're considering a generic extensive state function. This may be internal energy or enthalpy or Gibbs energy. We'll also look at volume in this discussion. That can be thought of as a function of temperature and pressure, just like normal. But now that we can change the composition of the mixture, the number of moles of each component is also a variable that we can play around with. And so when you're considering how does this extensive state function change, well, you need to consider changes due to temperature, that's this first term, changes due to pressure, and then here we have a sum of terms where each term reflects the change in that extensive state function with respect to changing the number of moles of that component. This derivative here is called a partial molar quantity. And we use a notation that looks like this. So whatever state function you're talking about, if this were enthalpy or Gibbs energy, it would just be H or G, subscript J, where that notation tells you to take the total Gibbs energy and take the derivative with respect to the number of moles of component J, keeping temperature, pressure, and the number of moles of every other component fixed. This is an intensive quantity. X, by definition, is an extensive state function. Number of moles is extensive. The ratio of the two gives you an intensive quantity, and we call these partial molar quantities. What we're doing here is we're eliminating the terms involving temperature and pressure. So if temperature and pressure are constant, then these first two terms will vanish, leaving us with just the sum over the partial molar quantities. And so that's what we have here. We're going to do a little bit more work on this expression by introducing a math trick of sorts. We are going to introduce a size parameter lambda, which takes us from a system of zero size to a system of full size. So think of this as like messing around with how big the system is. Lambda varies from 0 to 1. When lambda is 0, the system has 0 size. When lambda equals 1, it's at the full size. And so we can introduce a change in the number of moles of component J by taking the number of moles of component J when the system is at its full size and multiplying by this d lambda. And then to get what that allows us to do, if I take this expression that we have and substitute in for the number of moles of J, for the change in the number of moles of J, I get this expression here, which can be factorized out of the sum. The nice thing about this math trick is it takes all of these different variables, all of these different nj's, like for each value of J, for each component in the system, it's a separate variable. The nice thing about this math trick is that it puts all of those variables on an equal footing and allows us to factor out the d lambda. Then what we do is we integrate both sides of this expression here. So we'll integrate the extensive state function's total differential from 0 to the full value of the state functions. And then this part doesn't involve a differential. We just integrate lambda from its 0 value to its full value. Okay, this is a very simple integral to do. And so we get this definition here. So the value of an extensive state function is just a sum of all of the partial molar quantities weighted by the number of moles of each component. And this is a fundamental relationship that we're going to use throughout this focus. Let's look at a specific example. So we will consider the volume of a solution. And what I'll ask you to do now is to think about some of the general chemistry problems, maybe even quantitative analysis problems that you've worked with in the past. You may recall seeing a problem that has at the end a little bit of a disclaimer where it says something to the effect of, assume the solutions are additive. For example, if you're mixing a solution of one concentration with a solution of a different concentration, and then it'll just say, assume that the volumes are additive. Now, the reason why they put that in there is because that in reality, when you add liquid volumes together, they aren't simply additive. Okay? So the total volume is not necessarily a sum of the two volumes that you've added together. The reason for that is due to intermolecular interactions between the different substances that you're adding together. Depending upon how attracted the two liquids are that you're mixing together, the solution volume may contract. Or if they're not as attracted to each other as they are to themselves, then you might expect that the solution volume will expand a little bit relative to the two components that you've added together. Now, we're not talking about big differences in volume here. Typically, they're actually quite small, but they are measurable. So what we find then is that the total volume of a solution is actually a function of the number of moles of each component that you add together. And what we're going to introduce here are partial molar volumes. Okay, and so from that expression that we just looked at, that we just sort of derived, the total volume of a solution is a sum over all components of the solution, where you take the partial molar volume of that component and multiply by the number of moles of that component. Okay, so this is how you would go about, in principle at least, calculating the volume of a solution. You need to know the partial molar volumes of all of the components, and you need to know the number of moles of each component. Here's the definition of the partial molar volume. It's the change in the volume with respect to the change in the number of moles of that component J at constant temperature, pressure, and keeping the number of moles of every other component fixed. This is an intensive quantity. Okay, so this doesn't depend upon the size of the system. However, the total volume will. I'd also like to point out that the partial molar volume is not a constant. Okay? It depends upon the concentrations of all of the solutions. So this, of all of the components of the solution. So this quantity, this partial molar quantity, itself is a function of the number of moles of every component of the system. Here is a graph showing us the partial molar volumes of ethanol and water in an ethanol and water solution. We're plotting the molar volumes as a function of the mole fraction of ethanol. So here on this side of the graph, there is no ethanol present in the system. On the other side of the graph, it's pure ethanol. So over here we have pure water, and over here we have pure ethanol. So this red curve here, this is the partial molar volume of ethanol in water. And notice that the scales on the two sides of the graph are different. So the right-hand side of the graphic corresponds to the ethanol curve, and the left-hand side of the graphic corresponds to the water curve. And so when you've got pure ethanol, the molar volume of water is a little bit larger than 58 milliliters per mole. When you've got pure water, the molar volume of water is about 18 milliliters per mole. And as you change the composition of the solution, you see that so here, starting with pure water, you see that as you start adding a little bit of ethanol, the molar volume, the partial molar volume of water increases and then it decreases. When you're starting at pure ethanol, you see that as you start increasing the amount of water, as you go this direction, you see that the partial molar volume of the ethanol drops. It goes through a little minimum here, and then it goes back up to this value in the dilute ethanol limit. One thing that I would point out to you that may or may not be hard for you to see is that the two curves are in fact correlated with one another. Not perfectly correlated, of course, but you'll see that when the water molar volume goes up, the ethanol molar volume goes down. When the ethanol molar volume goes up, the water molar volume goes down. This graphic is illustrating how the partial molar volume works with respect to the total volume of the solution. So here we're plotting the total volume of a solution as a function of the amount of moles of component J, and the partial molar volume is defined as the slope of that curve at that particular number of moles of J. So this slope here represents the partial molar volume of component J for this particular composition. Notice that it's got a positive slope, so the partial molar volume is a positive number. Over here, there's a negative slope, and so the partial molar volume of component J would be negative for a solution with this amount of component J in it. Here we have a problem to work out involving partial molar quantities. So we're talking about a solution containing 1 propanol and water. It's at 293 Kelvin, and they are giving us the densities of these two liquids. And we're being asked to combine 100 milliliters of each liquid. We're then given the partial molar volume of both quantities, and they want us to calculate the total volume. And so we will use this formula that the total volume, is going to be equal to, I'll write it as a sum over all of the components. There's only 2. It's going to be the partial molar volume of that component times the number of moles of that component. Okay, so this is what they give us these numbers. We simply need to calculate the number of moles of each component. And so number of moles of component J would be the mass of component J divided by the molar mass of component J, right? Grams divided by grams per mole gives us moles. And then they don't give us the masses, but they do give us the densities. And so we can write this as the density of component J times the volume of pure component J. So I'll write that as Vj star, where this is not the partial molar volume. This is just the volume of component J that was used, and the star denotes that it was pure. Okay, so just working this out for this particular problem. We're going to have 2 terms, so I'm just going to lay out the numbers. So we'll start with the 1 propanol term. So we've got 72 milliliters per mole. The density of the 1 propanol, 0.803 grams per milliliter. That's times 100 milliliters. And then we need to divide by the molar mass of 1 propanol. So there's 3 carbons, 3 times 12.01 plus 16 for the oxygen, and then we're going to have 3, 4, 5, 6, 7, 8 hydrogens. So I'm getting a molar mass of 60.11. And then we're going to have a similar term for the water. So that's the water has 18 milliliters per mole. The density is 0.998 grams per milliliter times 100 milliliters. Divide that by 18.02 grams per mole. And then so we'll just run these through our calculator. And I'm getting 195.9 milliliters. So you take 100 milliliters of 1-propanol and 100 milliliters of water, add them together, and the solution will then have a volume of 195. So you see that it's a little short, right? It's not 200 mils. The solution is contracted compared to what you would expect if the volumes were perfectly additive. And what that means is that the interactions between 1-propanol and water are such that they are more attracted to one another than they are to themselves. And so this causes the volume to be smaller than you would expect. Of course, the opposite can happen. You can mix two liquids together, and the interactions between the two different liquids are different. They're not as attractive. I'm not saying they're repulsive. They are attractive. They're just not as attractive between one another as they are to themselves. And that causes the volume to expand a little bit. So by looking at the total volume, you can make a comment about the nature of the interactions between the two liquids. Here we have another problem. Okay. We're being told that we've got now a water-ethanol mixture. It contains 1 kilogram of water. And essentially, the polynomial function that's given to us is they're telling us what the volume is as a function of the number of moles of ethanol. And I don't know. The reason why they've used these funny definitions of nu and z is just to eliminate certain complications with the units. But essentially, nu is the volume in units of milliliters, and z is the number of moles of ethanol in units of moles, essentially. And so what they want us to do is to determine the partial molar volume of ethanol. And so what you would do would be to take the derivative of the volume with respect to the number of moles of ethanol, keeping temperature, pressure, and number of moles of water fixed. That is equivalent to evaluating the first derivative of nu with respect to z. And this is a polynomial of degree 3. When you take the derivative, the constant term goes to 0, and you're going to be left with the 54.67 minus 2 times 0.369 times z. And then you'll have, for the last term, plus 3 times 0.028 times z squared. So just taking the derivative of a simple polynomial, that's the answer. And what it highlights now is that the partial molar quantity, so this is VE, it in turn is a function of the number of moles of ethanol. Okay, so the partial molar volumes, even though they kind of indicate in this problem that they're constant, they aren't actually constant. If you change the concentrations, or if you change the composition of the mixture, the values of the partial molar quantities will change. And here's a plot of this quadratic function for the present problem. Here we have another problem. So in this problem, we've got at 25 degrees Celsius, we've got an ethanol water solution that's 50% mass ethanol and 50% mass water. They've given us the mass density of the solution. They've given us the partial molar volume of water. And they say, what is the partial molar volume of the ethanol? Well, let's think about that. So we've got the volume of the solution is going to be equal to the partial molar volume of the ethanol times the number of moles of ethanol plus the partial molar volume of the water times the number of moles of water. Okay, now we know the concentration of the solution, it's 50-50, and we know the mass density of the solution. So what we need to do is to make an assumption here, and you do this all of the time when you're working with solutions and concentrations. So since we know that this solution is 50% by mass ethanol and water, let's just assume, for simplicity, assume 100 grams of solution. That does two things for us. First, it allows us to calculate the volume of the solution. Because we know the density, we can calculate the volume of the solution. So that allows us to calculate V. Likewise, since we know that it's a 50% mass ethanol water solution, if we have 100 grams of solution, that means that we have 50 grams of ethanol and 50 grams of water. And since we know the molar masses, or at least we can calculate the molar masses of ethanol and the molar mass of water, that means we can get the number of moles of water and the number of moles of ethanol. And so, let's see here. We've got 2 carbon atoms. We've got an oxygen atom. And we've got 3, 4, 5, 6 hydrogens. So 4608 grams per mole. So those are our molar masses. We'll need those. Let's see. What they gave us the partial molar volume of water, and they want us to find the partial molar volume of ethanol. So I'm going to rearrange it. It's going to be V minus VW times NW divided by NE. The volume of the solution is going to be the 100 grams divided by 0.914. We'll subtract from that the partial molar volume of water, 17.4 centimeters cubed per mole, and we need to take that times the number of moles of water. So we'll take the 50 grams and we'll divide by 18.02 grams per mole. And then that whole thing needs to be divided by the number of moles of ethanol which will be the 50 grams of ethanol divided by the 46.08 grams per mole. So I'll run this through my calculator here. And if all went well, I got 56.2, and that's going to be centimeters cubed per mole. Hopefully I didn't make a mistake. Okay. Well, that was partial molar volume. And what we're going to turn to next is partial molar Gibbs energy. And this is a more important partial molar quantity because, as we've learned, for conditions of constant temperature and pressure, which are the most common conditions that we work with in the laboratory, it's the Gibbs energy that determines spontaneity. It's the Gibbs energy that determines the maximum amount of work, non-PV work that you can get. And so Gibbs energy and partial molar Gibbs energy is the most important partial molar quantity. And it has a special name that we've already learned. It's called the chemical potential. Now, it's a little bit different than what we worked with in the phase transition focus. There we had only one constituent. We had only one substance. We had a pure substance. And so there, the chemical potential was simply the Gibbs energy divided by the number of moles. That is, the chemical potential for a pure substance is just the molar Gibbs energy. But when you have mixtures, we need to speak in terms of partial molar Gibbs energies because the number of moles of a given component is a variable. So the definition of chemical potential in the context of mixtures and later chemical reaction mixtures, this mu J here, the J denotes the partial derivative of the Gibbs energy with respect to the number of moles of component J, keeping temperature, pressure, and the number of moles of every other component fixed. Again, if temperature and pressure are constant, then the differential of G can be written in terms of just this sum over the chemical potentials and the changes in the number of moles of each of the components. And as we did with that for in the generic case, using that system size variable lambda, you can do the same trick. It applies to Gibbs energy as well. And so this is how you could imagine calculating, at least in principle, the Gibbs energy of your system. You need to know the chemical potential of each component and the number of moles of each component. You add those together, you multiply those together and add up over every component, and that's what the Gibbs energy is. The Gibbs energy is particularly useful because it represents the maximum amount of non-expansion work that you can do when you're changing the concentration. And so this is important in applications involving electrochemistry. Sadly, we won't have time to cover electrochemistry in this course, but it's certainly of primary interest. This diagram reflects what we've seen previously. Okay, so this curve is the total Gibbs energy as a function of the number of moles of component J, keeping all of the other components fixed. You see that the Gibbs energy indeed changes with the number of moles of component J. And then the slope of the Gibbs energy curve represents the partial molar Gibbs energy, or it's what we call the chemical potential. Okay? And you see that the chemical potential for different concentrations is different. So the slope changes as you change the number of moles of component. So the point being that this quantity is also a function of the number of moles of each component. So this slide points out that although we have taken temperature and pressure to be our variables of interest towards defining the chemical potential in terms of Gibbs energy, there's really nothing special about Gibbs energy from a theoretical perspective. Although it may be experimentally more convenient to work with, you can define chemical potential, it's the same quantity, in terms of internal energy, enthalpy, or if you prefer, Helmholtz energy. It's all the same quantity. It's just a matter of what variables do you want to use to describe your system. You'll notice that in each of these different definitions, the natural variables for the potential function of interest are kept constant. Let's see. I want to actually hop back many slides. So we're going to go back to the introduction. I want to point out something that I couldn't fully explain before. It's slide 19. I'm now in a position to explain this last bullet point, but I'm going to go through the whole thing here. We've been looking at different types of thermodynamic contacts in some of our example problems. So for example, when we talked about a heating problem, you're talking about thermal contact between a system and its surroundings. And depending upon the nature of the boundary between the system and surroundings, you may or may not get heat flowing. In the case where the system and surroundings are at different temperatures, the conjugate variable to temperature is entropy. Right? So we have an intensive variable and an extensive variable, temperature and entropy. When the temperature between the system and surroundings are different, so when the intensive variable is not the same in the system as it is in the surroundings, what's going to happen is that energy is going to flow. When you have thermal contact, it flows in the form of heat. And that heat will continue. The system will undergo spontaneous change until the temperature between the system and the surroundings is the same. And as a consequence of that, the entropy of the two will change. The system and surroundings entropy will change as well. For mechanical contact, that is when a system and surroundings are joined by a movable wall, here the variables that we consider are pressure and volume. Pressure is intensive, volume is extensive. When the pressure within the system is different than the pressure in the surroundings, what you're going to have is spontaneous change, and energy will be transferred between the system and surroundings via work. And that will continue until the internal pressure equals the extensive pressure, and as a consequence, the volume of the system and surroundings is going to change. Now that we're talking about mixtures and later chemical reactions, we're talking about a third type of thermodynamic contact, so-called diffusive contact or chemical contact, which occurs when you have a permeable wall, a permeable boundary between the system and surroundings. In the case of diffusive contact, we have the chemical potential, which serves as the intensive variable, and the number of moles, which serves as the extensive variable. When the chemical potential within the system is different than the chemical potential in the surroundings for that species, you're going to have spontaneous change occur as long as there's a permeable wall. And then the amount of energy transferred is going to be mu times the change in the number of moles of that substance. That change will continue to occur until the two chemical potentials between the system and surroundings are the same, and as a consequence of that, the number of moles of that component in the system and surroundings will also change. Okay, so there's this underlying structure that's common between these three different types of thermodynamic contacts. So now I gotta fast forward and find my place. Too many slides, right? Man, we've already covered a lot of stuff. Not quite that much stuff. No, gotta keep going. Still in chapter 3. Okay. Getting closer. Here we go. All right. So that's what I wanted to say about the natural variables. How much do we have left here? Okay, that's where I was going to stop. So the Gibbs-Duhem equation, what we're going to be talking about here is the relationship between the chemical potentials of different components. This holds for all types of partial molar quantities, so it's actually a general relationship. So here's the definition that we've been working with, and we also worked with this one here. What I want to point out is that there's an apparent inconsistency between these two. So for example, if I take this equation here, which is true, and if I take the differential of x, I'm going to get a sum over two terms. I'll get xj times the differential of nj, and then I'll get another term, so it'll be plus nj times the differential of xj. Now, both of these equations are true, and if this is also true, that means that this second term, when you add up over all j, it must vanish, and it does, and that's what's called the Gibbs-Duhem equation. And what the Gibbs-Duhem equation does is it tells us that changes in the chemical potential of one component, or changes in the partial molar quantity of one component, are related to changes in the partial molar quantity of another component. And so that's illustrated here. We'll just consider a binary system containing two components. And then this is the expansion of the Gibbs-Duhem equation. And what it tells us is that a change in the partial molar of B is related to a change in the partial molar of A. And notice that there's this minus sign here. So if this guy increases, then that guy's going to decrease, and vice versa. Let's see, did I have anything else? Oh, okay, so how to explain this? So it's not just the signs that are opposite. Let's suppose that a small change occurs in XA. And for the case where this ratio is large, then the change in XB will be large. And so we can illustrate that here. Look, if you look, there's a small change in the partial molar volume of water. There's a corresponding big change in the partial molar volume of ethanol, and it's the opposite sign, right? This goes up a little bit, this goes down, relatively speaking, a lot more. And then you can use these partial molar quantities. For example, let's suppose you're studying a dilute solution or a solution with a non-volatile solute. It's very difficult to study the solute in that case, where it's a non-volatile solute. And so you can take advantage of the Gibbs-Duhem equation since it's easier to monitor the solvent. Information about let's just call it the chemical potential of the solvent, leads to information about the chemical potential of the solute. I didn't look very closely at this problem, so I don't even know if I know how to do it. If the composition of a mixture is such that the number of moles of component A is twice the number of moles of component B, and a small change in composition results in mu A changing by 1 joule per mole, then calculate the change in mu B. Well, let's just go to the Gibbs-Duhem equation. This would tell us that the change in the chemical potential of component B, so I'm just working from right here. The change in chemical potential of component B would be equal to minus the number of moles of component A over component B times the change in chemical potential of component A. And now the problem tells us that change in the number of moles of chemical potential of component A is 1 joule per mole. And then the composition ratio, right? So this is going to be minus 2 times. So what we'd find is if the chemical potential of component A increases by 1 joule per mole, then the chemical potential of component B will decrease by 2 joules per mole.